Hello everyone, this is Calc, and we're back with the second pair of the 2017 ARML individual round. You guys know the drill at this point. So, let's go right now. Number 3, we've got two quadratics that have one root in common. Our quadratics are x squared minus bx plus 36 and x squared minus ax plus 24. Now, polynomial factors work a lot like integer factors. If you add and subtract and multiply by a constant, it's not going to change whether or not it's a factor. So if these two have a factor in common, I can do some subtraction, get a minus bx plus 12. This has the same factor. So we know that this factor, this root, has to be negative 12 over a minus b, or 12 over b minus a. Now, we're told that we're looking for integers a and b. So we know b and a are integers, so b minus a is an integer, so this is rational. So we know we're looking. So what we need to do, since it's rational, is use rational root theorem to figure out what it can or cannot be. So it's 12 divided by an integer, or could be positive, could be negative, and it has to be able to divide both 36 and 24. The 1 doesn't really matter. In fact, the fact that these are 1 indicates that 12 over b minus a is going to be an integer, and it's an integer, it divides both 36 and 24, so it divides 12. You know, greatest common divisor and all that. So we've got an integer, positive or negative, that divides 12. So the positive ones are 1, 2, 3, 4, 6, and 12. You can check 2 squared times 3 is our factorization, so 2 plus 1 times 1 plus 1 is 6. So we're good so far, and then we include positive or negative. That gives us a total value of 12, which is the answer. So that problem was actually a really easy one, and now we move on with only about 2 minutes taken up to our second problem. It's another geometry one. They were really fond of geometry this year, or you might have noticed if you were there, or if you've looked at the test at any point. So we've got triangle ABC. Angle A has 90 degrees, so we've got A, B, C. We know that AC equals 1, AB equals 5. And we're looking for D on AC, so on the ray AC, such that DBC is double CBA. Or, yeah. So I put it like this. Say this is 2 theta, this is going to be D. So there are multiple ways to do this. I actually did it 2 different ways because I had so much time after number 3. I'm going to show you the simpler way, which is actually one I didn't use. Should I use that? Yeah, I'm going to use the complex numbers fashion. So I'm going to rotate this a little. 5, 1, double angle up to here. I'm going to write these out as complex numbers. So this is going to be our origin 0. This is going to be 5, and this is going to be 5 plus I. So we know that the tangent of the angle is going to be the imaginary over the real. And we know from de Moivre's theorem, or whatever, that if we want to multiply the angle by n, we just have to take our complex number and put it to the power of n, and that's going to have n times the angle. So we want triple angle because 1 plus 2 is 3, obviously. So we're going to cube 5 plus I. So we get 125 plus 3 times 25 times I is 75I. Right? Plus 3 times 5 times negative 1 is minus 15. And then in I cubed is negative I. So we've got 110 plus 74I. So our tangent is 74 over 110. We know that at our bottom is 5, so we're looking for our top, which is going to be 74 over 22, or 37 over 11, which is indeed the answer we were looking for. So, that was rather fun. We went through both problems in about 5 minutes, so about half the time we would actually need. So while we still have time, we can check this in a different way. The way I ended up using for my second way, it's a little bashier, but if you know angle bisector theorem, but it just involves angle bisector theorem and Pythagorean theorem. So we got 5, 1, x minus 1, and the square root of x squared plus 25. Now, why would we want all this? It's because by angle bisector theorem, I'm cutting this in half, by the way, so this is theta, this is theta, this is theta. So we have all of this. We have the square root of x squared plus 25 over x minus 1 equals 5 over 1, or 5x minus 5 is equal to square root x squared plus 25. X squared plus 25 equals 25x squared minus 50x plus 25. And then we can keep going with that, and we find that x is equal to, move this over, or here for 50x, 24x squared, 24 over 50, or 12 over 25. Wait. No way, I did that backwards. It should be 25 over 12. My mistake. So we've got 25 over 12, which means this is 13 over 12. And this is whatever. We don't care about it anymore. What we do care about is that this is root 26. This is y minus 25 over 12. And y is what we're looking for at the end. And this is the square root of y squared plus 25. So we're going to do what we just did. This is 25 over 12, this is 5, so we get 5/12 is equal to y minus 25 over 12 over the square root of y squared plus 25. We move stuff over, we get y squared plus 25 equals, you square this, we get 5/12 y minus 25 over 12, 5/12, so that's like 125 over 144, which, yeah, that checks out. Squared, and honestly, if you want to do the rest, you can. I did it during the test, and it did come out to the right answer at the very end. But when I say the very end, I mean the very, very end. So you guys can have fun checking the work. Tell me if I did anything wrong, which, you know, whatever. Which, by the way, I did. It should be 13 over 12 over root 26. You know what? We have more than a minute left. Let's just finish this off really quick. Y squared minus plus 25 over y minus 25 over 12 equals 13 equals root 26 over 13 over 12. So I can write that as 12 root 26 over 13. And then, once again, you can do the rest of the math for yourself, because I've got less than a minute to do it, and to be honest, it was long and unnecessary, and we already have a good way of doing it. But honestly, it helps to know multiple ways, so if you have extra time, you can check yourself. Anyways, I hope you enjoyed this. The next one should be coming out relatively soon, so be sure to like, comment, subscribe, share it with anyone else you think would enjoy this, and yeah, I will see you in the next one. Bye-bye.